before we might. Okay. Okay, let's start again. Okay, so the first problem, um, it says, okay, so there's some sort of story which makes absolutely no relevance to the problem. And then it says the problem is simple. For given n, find the number of odd coefficients in the binomial 1 plus x raised to the power n, but there's a catch. N can be as big as 2 billion. Okay, the only line in the input is an integer n, which is between 0 and 2 billion. The degree of the polynomial of 1 plus x to the n, for which you need to determine how many of its coefficients are odd. Okay, so that's the question. So I guess, the first thing is maybe for small n, let's say n is equals to, I don't know, 6. Then first thing that you have to know is that this expands into something like this. 6 to the 0 times x to the 0 plus 6 to the 1 times x to the 1 plus 6 to the 2, sorry, not to the 2, 6 choose 2, x to the 2 plus 6 choose 3. So it's just all the binomial coefficients. Or if you want, you can say that if you look at a row of Pascal triangle, these are all the numbers in this row, and the row number 6. And out of all these, 6 choose 0, 6 choose 1, etc., you want to know how many of them are odd. Okay? So the question, of course, is how do you know, how do you count how many of these things are odd? And if n is small, you can just compute all these binomial coefficients, no problem, and then you just count them. And or you can even say, how do you compute binomial coefficient? One of the ways to do a Pascal triangle, and then Pascal triangle is always the sum of the two things on top. Why am I writing 0? Because I'm computing the Pascal triangle mod 2. So if I do it like this, I will see something like this. And maybe you'll find a pattern. I don't know. So you can kind of play along with this. And maybe you'll find a pattern. Maybe you'll try to construct this Pascal triangle, but there's just no hope that you'll ever succeed because it's 2 billion. You'll run out of memory. Whatever method that you use to try to directly compute these things, it's going to be hopeless. So then, you would say, maybe if you don't know, you would say, okay, binomial coefficient. This is what I search, and then I kind of look at this, and then there's a paper here. There's something else here, but then there's this thing called from Geeks for Geeks, which has code. So this is the link that you can, and then there are lots of other places you can look, and this is one of the places. It doesn't tell you why, it just tells you here's the code. So here's the code, you copy it, and that's it. That's the end of the story. Well, that's not very satisfying, I guess. It also tells you that the count of odd binomial coefficients are equal to 2 raised to the power of the number of 1 bits in the binary expansion of n. So what it's saying is if n, okay, so if n is, let's say, I don't know, 10 in decimal, then this is actually 1010 in binary. So there are 2 1s here. So that means that it's 2 to the 2 equals to 4. That's your answer. Okay, it doesn't tell you anything about why. It just tells you here's the solution. That's it. So I guess at this point, in a real contest, well, I guess in a real contest, you wouldn't have this online search. But since you have the online search, in a real contest at this point, people that have found this, paste the code and submit it, and that's the end of the story. That's why you have so many people getting it so quickly. But a lot of people don't even know why it works. So there's something called Lucas theorem, which says that this is something in number theory, and there's even proof that I'm not going to go through. But basically, it says that the binomial coefficient, it's equals to something like this. Mod, let's set p is equal to 2. So p is equal to 2. So we'll just pretend this is 2. When you write the binary expansion of m and n in base 2, then somehow the binomial coefficient, so let's say you're looking at, I don't know, 10 choose 7. Okay, so 10 is 1, 0, 1, 0, base 2, 7, 0, 1, 1, like this. Then it's saying that this is the same as 1 choose 0 times 0 choose 1 times 1 choose 1 times 0 choose 1 mod 2. You can somehow look at each of the bits and do this binomial coefficient this way. And if any one of these is 0, then the whole thing is 0. So with 0, that means it's even. And the only way that this is odd is if every one of them is odd. So what that means is that if you want this to be odd, whenever you see a 0 here, this must be 0. There's no choice. It must be 0, because if it's 0 choose 1, then it's 0. The answer is 0, and then it's even. So if it's 0, you must make it 0 so that this 0 choose 0 becomes 1. And then if you have 1 here, then it doesn't matter if it's 1 choose 0, 1 choose 1, it's always going to be 1. So every time you have a 1 bit in the binary representation of the top, you can, on the bottom, you can choose either 0 or 1. And so the number of times you have 1 bit raised to the power is 2 raised to the power of number of 1 bits, number of ones. That's the number of binomial coefficients that are odd. Okay, so I know that most people that submitted the solution and got it right probably didn't even know this, and probably most of those people don't care, but this is where it comes from. Now, of course, I haven't told you the proof of Lucas theorem. This is something that I don't know, even if you take number theory, I don't know if you'll even talk about this in your elementary number theory class. This is something maybe a bit more advanced. Anyway, wait, Julie, are you in the number theory class?
No, not yet.
Not yet. Okay, so maybe let's see who else.
I am, and I don't
think I'm
gonna cover it.
Yeah, so yeah, this is something that's quite advanced. And so this is unfortunately, I think, a pretty unfair question. It's, I guess, for a, how do I say, for a normal contest, you would see very few people getting this problem. But because the contest now is online and people can look things up, this turns out to be extremely easy because you can just find the code online and just submit it. There's not really been a big challenge. So that's unfortunate. I'll just quickly show you my code. So here's my code, and the only reason I want to show this to you is to show you how I compute the number of ones in a binary representation. So in G++, this is non-standard C++. This is only in G++. There's a function that's called __ built-in _ pop count. And this will take a number and return the number of ones in the binary representation of that number. So I didn't even have to do anything to compute. I just tell G++ to give that to me. And then if I take a number 1 and right shift it to something, then in binary, I'm basically writing n zeros here. And in decimal, that's equivalent to 2 to the n. Okay, so it's just like in decimal. If I left shift a number in decimal by adding zeros, let's say I add 3 zeros, that's the same thing as 10 to the 3. So when I left shift 1 with n position by adding n zeros to the binary representation, that's the same thing as 2 to the n. And then the last thing that I have to be careful is that I need to make sure that I don't overflow. So if I just write one arrow n like this, then this is going to be by default a 32-bit integer, a normal int. But when I say 1 ULL, this is saying to C++ that I want this number to be treated as unsigned long. Okay, so that makes sure that I don't get overflow. But anyway, that's basically it. There's not really too much more to say, unfortunately. That's it. Any questions? Yeah, this is a terrible problem. I think everybody, I mean, I was kind of on the periphery in terms of the organization of this contest, but I was in the chat room kind of watching what the people in the Calgary judging room were saying, and everybody was kind of surprised that this problem was solved so quickly and so by so many. And well, it didn't take us long to realize why. So anyway, so that's that. It's not very interesting problem at the end because you just look it up. All right, so then the next problem that I guess the easy problem is star battles. Star battles. How do I get star battles? No. Okay. The thing is my what do you call it? Zoom thing has a little toolbar on top that kind of block my tabs. Okay. Okay. Here we are. Star battles. Okay. So this is actually the easiest problem in the contest, even though it looks kind of scary. So a star battle, the two-star variety, also known as Two Not Touch, is published by the New York Times, is a solitary star placement puzzle played on a 10 by 10 grid. The grid is divided into exactly 10 connected regions. So what is 4 connected? It means that a square is connected to the 4 neighbors on the top, bottom, left, and right, but not diagonally. Okay, so here, this is a region, but these two cannot be connected this way. Okay, so the grid is divided in exactly 10 connected regions, and the objective is to place exactly 20 stars in a grid, each in its own cell, such that the following conditions are satisfied. Okay, every row, column, and region of the grids contain exactly 2 stars. So in every row, this row has 2 stars, this row has 2 stars, and so on. Each column has 2 stars. So this column has 2 stars, this column has 2 stars, and so on. And each region also has 2 stars, exactly. Also, no 2 stars are in adjacent cells, i.e. cells next to each other horizontally, vertically, or diagonally. Okay, so no 2 stars can be next to each other, even diagonally. Below is an example of a star puzzle where regions are delimited by both lines. The unique solution is shown on the right. So here's the solution. So what is the problem? The problem is you are given a description of the puzzle, so the thing on the left, and a candidate solution. Your task for this problem is to write a program that will determine whether or not the candidate is indeed a valid solution to the puzzle. The input of your program is guaranteed to be a valid star battle puzzle with a unique solution. The last part actually doesn't really matter. You're not trying to solve the problem, so you're just asked if the solution makes any sense, right? So the first 10 lines of inputs contain a description of the star battle puzzle. Every line contains exactly 10 digits, where the digit names the region to which its cells belong. There'll be exactly 10 contiguous connected regions in the puzzle. So just quickly, it looks kind of like this. Maybe let me make it a little bit bigger. So the first region has all the zeros, and then all the ones form a region, all the twos form another region, and so on. And then the next 10 lines gives you the solution, the candidate solution. The dots are empty and the stars are, of course, where the star goes. And then you have to basically read this input and say, is it a valid solution or it's not a valid solution? Okay, valid or invalid. So in terms of what you have to do here, because the puzzle is actually really small, 10 by 10, there's no real difficulty in terms of the computational time. Most reasonable approach you want to do will run in time. The main thing is you have to make sure that everything that you have here is taken care of. Okay, so what do you do? Right? How do you do this? Well, when you have, so you probably have an array of characters. So I don't know what you call this. Let's call it solution 10 by 10, let's say, and make it a character. Okay, and then here you have this. You don't have an array of. I guess you have an array of numbers, right? You have something like this, etc. This is what you have. Now, I think I call it region. I don't remember what I call it. Doesn't really matter. And I decided to use an integer to store the type, to store the this array. But one of the problems is that when you read this in, these are not integers. You just get a string of these 0, 1s, and 2s, and whatever number. So what you get is actually character 0, character 1, and so on. How do you convert it to an integer? If I want to take the characters that you read and turn it into 0 to 9, what is a good way of doing it? Anyone?
I kept, no, what did I do? I
Yeah,
feel
I
like
know what you did.
Okay, you know what I did? Okay.
I saw what you did, but
Okay.
Okay. Does anybody want to say anybody else want to say anything? Okay, so now Luke, you tell everybody what you did.
I'm pretty sure I subtracted the ANSCII code.
Okay, so you have some character, you read in a character, and then you say something like region ij
Yeah,
is equals to ch minus
48.
48.
Yeah.
And what is this magic 48? Where do
Oh,
you
yeah.
get this 48 from?
Like the ANSCII, so like I'm pretty sure 0 is the ANSCII code, 48.
Okay.
And then I
Okay,
think
so the
that's what
ASCII code of the character 0, right?
Yeah.
So this is correct, but I don't like it, and I'll tell you why. Because you have to remember what 48 is, and everybody has to remember what 48 is.
Mm-hmm.
Just write this.
Oh.
That is the ASCII code of 0. So if you use a character, so in C++, characters is actually an integer type. And if you use it in arithmetic, it will automatically use the ASCII code of the character. So you don't even have to remember what this is. I don't remember what this is 48. In fact, I have no clue because I never care. I just write this and then it's all good. Okay?
Okay.
So that's and then similarly, for example, another common thing is if you have A, B, C, like the lowercase letter, let's say, and you want to convert it to 1 to 25, you can use CH minus the letter A with quotes on it, and that will convert the characters into the numbers from 0 to 25. Okay, so it's the same idea. And again, the good thing is you don't have to remember what the ASCII code of A is. Okay. Anyway, that's a small thing. Okay, now what do you have to do? You have to know that every row and every column and every region has exactly 2 stars. So how do you do this? Well, you could have an array I don't know, row, the 10 of them. And at the beginning, you initialize all of them to 0. You can have an array, 10, and even a region count. Initialize all of them to 0. Then every time you see a star, you look up which row it is, you look up which column it is, and then you can increment that corresponding count in the array, right? What about region? Well, when you see a star here, you can go look up here to see that it's region 1, and then you can increment the corresponding one here in this region array. And you can do that for all the stars, and at the end, you can make sure that every entry is 2. If any of the entries is not 2, then you know it's wrong, right? Now, it also says that you need to have exactly 20 stars, and that you actually don't need to check explicitly, because if every row has exactly 2, or every column is exactly 2, and so on, then it's automatically 20 stars. You don't have to check that explicitly, although it wouldn't hurt if you do. And then the last thing that you have to worry about is no 2 stars and adjacent cells. So what do you do? Well, basically every time you see a star, you have to look at your 8 neighbors around you and see if there are any stars. And if there are, you say no. Otherwise, you say okay. What about this one, right? This one, you try to look at the 8 neighbors around you, then you're in trouble because you are looking out of bounds. So what to do? Well, there are a number of things you can do. One thing is that when you do this, when you look with the 8 neighbors, you can say, well, only look at the neighbor if it is actually in bounds. So you do a little check to make sure that the coordinates are actually in bound before you look. Or you can just make everything bigger. Instead of 10 by 10, you artificially make the array bigger and just fill them with empty spots in the outside. So make sure that there are no stars anywhere on the outside border. And then whenever you have a star, you can safely look around you without ever worrying about going out of bounds, and without ever worrying about having your results affected by these cells, because you know that there are no stars in them. So this is a little trick that sometimes if you are worried about going out of bounds, you pad your array, or whether it's 1-dimensional, 2-dimensional, and so on, so that there's empty space around. And so you don't ever have to worry about going out of bounds. And you know that if you initialize these things properly, you never have to worry about these empty cells affecting your results. I think you did this, Luke, right?
Yeah.
Okay. So that's basically it. I can show you the code. Are there any questions before I do that? Okay, so let me show you the code. Okay, so I have the region. So this is going to store the regions. This is the solution that I read. I initialize everything as 0. 0 now, okay, this is a little bit tricky maybe. I write 0. Now this is an array of 144 elements, so 12 times 12, but I only initialize with one value. So in C++, if you put any value at all, doesn't matter what it is, you can put 1, you can put 10, whatever. But if you don't specify everything, there's 144, I only specify 1, then automatically it fills the rest with zeros. So even if I say 5 here, it will still be 5 followed by a bunch of zeros. It won't be 5 all the way through. Okay, so this is a little trick that we can use in C++, so we don't have to type 144 zeros. And then the other thing is, this is a character, and I'm putting 0. So this is the null character. It's a special character this is actually an invalid character. But I didn't really care, because as long as it's not a star, I don't care. Okay, so now I have to be a little bit careful because these are now my indexing. I have to be a little bit careful because I now have 12 rows and 12 columns. So the real data actually goes in row 1 to 10 and column 1 to 10. So in my loops, I have to be careful and loop from 1 to 10 and 1 to 10. Okay. So I read the character, and then the region is just the character minus the ASCII code of 0, as I said. Then I read the solution. Okay, and then I do the checking. So let's scroll down and see how I do the checking. Okay, so I have this flag that by default I assume that things are valid. I have row and column. This time I have 11 because I'm going to use row 1 to 10 instead of 0 to 9. And similar for columns, but regions I'm still using 0 to 9 because that's what they give me. And this initializes all the entries of the array to 0. Then for each element, I loop through the array. If it's a start, I just skip it. So if it's not a star, I don't do anything. So alternatively, I think most people that you hear from your class when they teach you how to do programming, they'll probably suggest that you write if C equals to star, then do all of this stuff in here, right? But instead, I'm testing the opposite and then using continue to skip the rest of the loop. And most people at the beginning programmers class and so on, they will tell you maybe they won't even teach you what continue is. But if they do, they will tell you don't use continue because it's confusing and so on. Is that what they tell you in these classes? I don't know. Anyway, but if you do that, then all this code that you write will be one level of indentation higher. And sometimes more level of indentation makes things harder to understand. So I actually write things the other way. I just say if it's not what I want, I continue, and then the rest of it I can keep going. This is sort of my main line of code. So what do? I update the counts for the row. So for this, I have one more star. For this column, I have one more star. For this region, okay, then I increment the counter in here. I have one more star. And then now I am going to say, okay, I look at this star. This is my RNC. Then I look at from R minus 1, so it's this row, to R plus 1, columns from C minus 1 to C plus 1. So it's this box. I'm basically looking at this box, and I'm counting how many stars I have. So if in this box I see a star, I do count plus plus. And what I want is to make sure that I only have one star, because I know there's a star in the middle. Otherwise, I wouldn't be doing anything. But if the count is not 1, then it's no longer valid. Okay? And if I really want to, I can break. Because once I know that it's not valid, there's no point continuing looking at anything else. And if I really want to, I can also do something like only continue these things with it's valid. So as soon as something is not valid, I break out. But anyway, because it's 10 by 10, it doesn't really matter if I search the whole thing. It's so fast anyway. So I didn't even bother making my code more complicated to save myself a few nanoseconds. And that's pretty much it. At the end, what do? I just so maybe I'm not valid already because I have adjacent stars, but I also at the end just check that all the rows have 2, all the columns have 2, and all the regions have 2. And then at the end, if my flag is still valid, it's still true, then I print valid, otherwise I print invalid. And that's the end of the story. Now, I'm not going to attach any names here, but you can, I suppose, notice that I am actually storing this, I'm storing this solution, stars and dots, and then I'm processing them. I could have, okay, I could have done all these processing up here. I could say if what I just read, it's a star, then I can update my row counter, I can update column counter, I can update this one, and then I could also try to look around while I'm reading it to make sure that I don't have an adjacent one. But there's a slight problem, and then it's not a huge problem, but it's a slight problem. So I'll be reading along, I'll be reading stuff like this, and then I'll read another one. Okay, and then maybe I keep reading, and then there's another star over here. So I can, of course, update the count of the rows, the columns, and the region. That's not an issue at all. But now I need to know, how do you figure out if you have adjacent ones? So the problem is I cannot just look at the eight neighbors because some of these haven't been read yet, right? So I might have a problem because I haven't read everything yet. However, what you can do is that you can make sure that you check these 4 neighbors. Those are the ones that you have read, right? So instead of looking for the 8 neighbors, you look for 4 neighbors. And then, what if you have a star here, but then you have a star here? So when you're checking this one, you won't see this one. But by the time you come here, you would be able to see this one, right? You can actually argue, I suppose, that this is more efficient than the way that I do it, because here, if you have a diagonal like this, you only be checking in this way. So you only be checking it once. Whereas the way I do it, I check it this way and I check it the other way. So I check it twice. And maybe it's I'm doing a bit more work than I need to. But again, I didn't really care because it's only 10 by 10. I just do whatever is simple. Okay, so I think that covers everything for this. Any questions on this problem? Comments? Any more comments? So this is, in some way, this is the easiest problem in the set, but it is definitely not trivial. I say it's easiest because they basically told you what to do. There's nothing that you need to figure out, I guess. You just do it, but you have to do it right. But it's just not, I have to write quite a bit of code. The first problem is simple in the sense that I don't have to write much code, but it's still not that simple. Okay, now what is the next one that so the next easiest problem, I suppose, according to, according to this, I think is, let's look at this. It's either print quota or predicting GME. Yeah, and which bits, it's also that. Also kind of apparently easy, but there are not that many people in the open division, so the numbers are a little bit misleading. Okay, so let's see which one we do. Okay, predicting GME, because I think one of our teams tried this, right? Is it Julie or Jana that tried this?
That was Julie.
Okay. Okay, so this is not an easy problem in the sense that it requires some knowledge of specific paradigm problem solving techniques. But for those that are kind of well established contestants, they will look at this and then just do it right away. Our team, I guess both Joseph and Josh, our top team, they both got it wrong a few times because I think the problem statement was unclear what you're supposed to do, what the problem was asking. But as soon as they posted a clarification, they immediately got it because they just changed the code to solve the problem that they meant to ask. Okay, so what is the problem? Okay, so you have a certain stock, this GameStop stock. I don't know how many of you have been following that the short squeeze. If you knew how that works, people were making money, and then at the same time, some people were losing lots of money. Anyway, so you have a bunch of stock prices, okay, for the next n days. So P1, P2, up to Pn. So somehow you know the stock prices for the next n days. And each day you're allowed to do exactly, well, not exactly, sorry, at most one transaction. Okay, you cannot do more than one transaction. You can decide to buy a stock. So I should say, maybe this is not the most accurate way to write it. You can one stock share. So if something is, if something has priced $10, you can buy one of those. That's it. Okay. And you can own, so this is the one that's unclear from the problem statement. You can only do this if you currently do not have stock. Okay, so you cannot be holding multiple units of stock. So you can't say I buy one share and then the next day you buy another share. You can only hold one share at a time. And then if you currently have a share, you're allowed to, you can sell the share. Okay, so if you buy the share, you have to pay whatever the price is for that day. And if you sell the share, somebody will pay you for that price for that day. Also, if you are selling, the next day you're not allowed to buy. So if you sell something, you have a cool down period. You have to wait for one day before you can do something else. Okay. And then write, Sarah, a program that can return the maximum profit while considering the restrictions put in place. So basically, you have, every day you have two choices. Well, okay, you have at most two choices. So each day, maybe let me use a whiteboard. Okay, so each day, there's at most two choices. Okay, so what are the two scenarios? If you hold a share, okay, if you don't hold a share, then there's nothing you can, then you cannot sell. If you hold a share, you can do nothing. You can keep holding it, or you can sell. And skip one day. Okay, that's because once you sell, you can't do anything the following day. Or two, if you don't hold a share, then you can again choose to do nothing. You can always choose to do nothing. Or you can buy. Okay, you can buy. And then the next day you can do whatever you want. Okay, you don't have to wait another day before you can sell. So those are the two choices. So what to do, right? So you have, so basically day 1, 2, 3, 4, up to, and you can always choose one of the two options, right? So if you hold a share, so if you hold or don't hold, well, what do? So on day 1, you don't hold a share. So I guess the day 1, this is not available. On day 1, you start with nothing. So you can decide to buy something or not buy something. So you basically try both. So you try to buy or you try to not buy. So if you imagine that I have some sort of recursive function f that says if I'm on this day and I have a Boolean, so this is a Boolean, whether I'm holding a stock or not, it's equals to the maximum profit I can get starting from this day and holding or not holding stock based on this Boolean flag. So at the beginning, what I want to compute is f of 1 false. So I want to start on day 1 not holding a stock. That's what I want to do. Okay, and then the question is how do I compute this? And so why do I start writing something like this? So typically when you have a problem where you have a bunch of days or a bunch of times or whatever, and each day you can make choices. Every day you can make some choice, and then once you make the choice, then you move on the next day. You can set up some kind of a recursion. Okay, so let's look at this situation. So if I am at a certain day, actually I'm just going to use D, so I don't have to write everything, and I'm holding a share. What can happen? Well, either I do nothing. If I do nothing, then basically I'm just moved to the next day and I'm still holding the share. Okay, so that's one possible scenario. Or if I sell something and skip a day, so skipping a day means that I go D plus 2. So because the next day I don't do anything, so I just skip a day. And then if I sell it, I no longer have it. So basically I sold the stock. I want to know after I sold the stock in 2 days, after 2 days later, if I don't have the stock, what is the best I can do? And then I also get the price for D, because whatever price is on that day, when I sold it, I pocket this much money. And what I'm going to do is I'm going to take the maximum of the two things. I'm going to take these two things and take the maximum. That's the best thing that can happen. So either I do nothing or I sell and skip the next day. Whatever that gives me, whichever one gives me the biggest number, I want to keep that number as the best in this case. Okay, before I go on, is there any questions about how I'm doing this or what this formula means? Okay, so in the other case, if I'm not holding if I'm not holding a share, then again, either I do nothing. So if I do nothing, then it's just basically I still hold the share. Sorry, I still don't hold the share. Or I buy. So if I buy, I now hold the share, but I lost this much money. I pay this much money. And this, of course, can be baked to cancel out what I have to lose to buy the share. And again, I take the maximum of these two. And then, of course, at the end, if I ever have, if D of anything, doesn't really matter, doesn't really matter what this is, it's 0 if D is greater than N. So if somehow I gone past the end days, and whether I hold the stock or not, it doesn't matter. I can no longer make any more money. So it's just zero. So that's my base case. So what I'm going to do is I'm going to start by computing f of 1 comma false, because at the beginning on this day 1 I don't have a stock. And then I'm going to recursively use one of these formulas to compute this. So this would try both of these branches on day plus 1 on day 2. And then when I compute these ones, one for false, one for true, they will recursively go all the way down. But notice that every time you see, for example, if I use this branch, I would always try to do 2 things, right? And then if I go this branch, I would try to do 2 things, but this time one will be here, but one will be kind of this way. We'll be skipping a day, and so on. The point is that whatever I'm trying to compute, let's say this one, day 3, while I already have a stock, I might be asked to do this one multiple times. And further on, and if you keep going, it will be, you can have something that get asked many, many, many times. So this is what you need to use dynamic programming, meaning that you will try to remember if somebody asks you, day 4 holding a stock, what is the optimal? You compute this if you have never seen it before, and once you computed it, you store the result. And if any time somebody asks you, again, the same question, day 4, you already hold stock, you check to see that you have already computed it, and you don't do all the recursion to figure things out again. And if you do that, then you realize that in this table, there are only n columns and 2 rows. So the number of entries is really just 2 times n. And each entry can be computed basically with just two computations plus a maximum. So this can be done in linear time, as opposed to possibly if you do it recursively without dynamic programming, it would be exponential time. So that's the solution. It's to recognize that you can do things one day at a time, and then once you decide what to do in the first day, you can just recurse. Yeah, okay, sorry, my dog is kind of going crazy here. Okay, anyway. Any questions about that and that before I can show you the code? Any questions? Okay, so let me get rid of this, erase everything, and then show you my code. Okay, here it is. Okay, so the way, I guess I switched the 2 parameters around, but that doesn't really matter. So I have the number of days and the price of the of each day, and I guess I do use global variables, so I don't have to bother passing it around to functions. And then I have this array, which is my array to remember whether I've computed this before. So my array would basically have the days. So I start from days 0 to n minus 1, and then I have basically 0 and 1. 0 means that I don't hold it already, and then 1 means that I already holding it. Okay, so I have an array like this, and I know that the answer, the maximum profit I can make, it's always going to be non-negative, because if I'm going to lose money, then I could easily just not do anything the whole day, the whole time, n days. Don't buy, don't sell anything, and I would be better off. So I know that the answer is always going to be at least 0. So I'm going to use -1 to indicate that I have never computed. So initially here, So I read in n, and then the first thing that I do is I just initialize this array to be -1. So if I see a -1, I know that I've never done the computation before. I read in the price, and then I said compute f of day 0 with, sorry, day 0, the first one. The first one is that I'm not holding a stock, and the second one is day 0. So here it is. The code is like this. If the day is bigger than or equal to n, so because I'm using 0 base, bigger than or equal to n means I'm out of bounds, then I no longer make any more money. That's it. Then I ask if the entry in the array is greater than or equal to 0. So if it's not -1, that means I've already computed it. So that's it. I just return it. I don't do anything else. This is actually, I don't think this is actually necessary. I'm just saying if this last day, if it's the last day, if I'm not holding anything, then the 0. Otherwise, I just sell it. I don't actually think this is necessary. I think that this would actually cover it. Okay. Now, basically, then what are my choices? I can always decide to do anything. Don't do anything. So I just keep whatever, whether I'm holding a stock or not, I just keep whatever that is and just move on the next day. That would always be one choice. If I am not holding something, then I can also choose to try to buy. So this is the same formula. If I buy, now I'm holding a stock, and I go to the next day and I lose this much money because this is how much I have to pay to get the stock. If I'm holding something, then I can try to sell. I would get this money. I would no longer have the stock, and I would have to skip to the next day, skip 2 days. And then I basically take the max along with the do nothing. And then basically that's the answer. So before I return it, I assign the answer into the array elements and return it at the same time. So the next time if I get asked this entry again, I would be able to just say it's done, so I don't have to do any of this recursion. Alternatively, you can decide not to do recursion because basically every single entry always look ahead, always look forward. So as long as things that are to your right in this table has been computed, you can compute the entry. So what you can do actually is to compute the entries backwards. And then whatever you're trying to compute, it's guaranteed that the thing that you need are always ahead of you. So it always has been computed. So you don't actually need to use recursion. You can actually loop the days backwards and compute it this way. But either way, it's dynamic programming. So that's how you're supposed to do this problem. It's definitely a little bit more tricky. There's more algorithmic knowledge and so on involved. So that's dynamic programming. Any questions? Okay, no, nothing? Okay, so now the next two problems, which one do I want? Oh, no, I want to know about which bits, because which bits is a little bit funny problem. It's a problem that many of you have never seen before, at least this style of problems. So this is what is called interactive problem. An interactive problem, so normally in most programming contest problems, you're given an input file, you program read the input file, does whatever it needs to do, the whole input file, you can read the whole thing if you want, or you can read a little bit of time, doesn't really matter, but the whole thing is available to you, and then you do your computation, and then you output the answer, that's it. But with interactive problems, you can send some output, the judges can give you some inputs, based on your output, and then based on the judge's input, you can send some other output, which then the judge can respond. And it's sort of a question query answer system. where you ask something, the judges give you an answer, and then you can decide to change your response, etc. And so it's a little bit different than what you're used to. So let's see. So you have the year 2025, and I don't know how to pronounce this, Eardria. By the way, has anybody figured out where these character names come from? Anybody?
Isn't that Airdrie?
Yeah, all the character names are kind of permutations, mostly the names spelled backwards of various Alberta places close to Calgary, I suppose. Anyway, so this character has just purchased the greatest new computer model with 2 to the 63 bits of RAM. Okay, the dramatic increase in RAM size from previous models is certainly welcome, but along with it comes some technical quirks. One issue is that the rather slow CPU was manufactured in 2005, which is unfortunately the best model available due to the ongoing COVID-induced CPU famine. To work around this, a feature was added to the RAM, enabling the CPU to query exactly how many bits are set between a given range of memory addresses. Okay, so your memory, it's between 0 to 2 to the 63 minus 1. You have that many bits. Okay, there are many, many bits. Some of them are 0, some of them are 1s. Okay, dot, 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 like this. And you have to figure out exactly which bits are 1s. Now, of course, if you have to answer the question when there are 2 to the 63 minus 1 bit, just writing it all out would take forever. But it tells you that Airdrie, or whatever you call it, has just performed a computation which sets as many as 2 to the 10 bits throughout the RAM and would like you to recover the addresses. The CPU is fast enough to perform 2 to the 16 queries while she's out. Okay, what are the queries? The queries that you can ask is from A to B. So you can give 2 addresses, and the answer of the query would be, in this range, how many 1s there are. Okay, and you know that there are only about 1,024, at most 1,024 bits that are set to true, that's set to 1. Okay, that's it. That's the problem. You're allowed to ask in each range, in a certain range. You decide which range you want to ask. Okay, and then the response is how many 1s are there in that range. Okay, so you may output up to 2 to the 6. So you're not allowed to ask too many questions. You're only allowed to ask 2 to the 16 questions. Okay, so what should we do, I guess? Okay, so how do you ask questions? The way you ask questions, you write Q followed by the beginning of the range and the end of the range inclusive. And then the judge will send you a number, which you can read as 3. And based on that, you can decide where you want to go next. Okay, and then at some point when you are sure when you're sure you know where the bits are, you write A followed by how many bits there are, followed by the index or the address of the bits that are set to 1. Okay. What should we do? So does anybody have any idea how we can try to start this problem? Okay, so 0 to, let's just make it small. Okay, let's just start from 0 to 10. See if we can have any kind of general ideas. And let's just say that there's exactly 1 bit that's 1. And you don't know where it is, but there's only 1 of them. Okay, now, of course, you can say, well, I'm just going to ask, right? I'm going to ask, what am I going to ask? I'm going to ask Q00, Q11, Q22, and so on. I ask 10 queries, each one just cover exactly one single cell. And if you do that, of course, you will get one of them to be 1, and you know exactly which one it is, because this one, all of these would tell you 0, but this one would tell you there's a 1 bit in this range, and so you know that there's a 1 bit here, and that's it. But that's not going to work, of course, if you're going to have 2 to the 63 locations. So is there anything that we can do that's smarter than just trying every single cell one at a time? Anybody? So what if I ask Q05? Okay, so what's going on with Q05? It's going to tell me 1. The answer is going to be 1. So I know that from here to here, there's 1, 1. But if I know that there's only 1, 1s, what do I know about this range? I know that there's nothing here. So I know that I never have to look at this again. Agreed? So if I know that I never have to look at this again, then I can play the same trick here, and I can ask, well, let's look at 0, 2. And it's going to tell me 1. So again, I know that I never have to look at this range again. 3 to 5. And then I say, well, okay, what if 0 to 1? It'll tell me 0. Then I know that I never have to look at this range again. And now I don't have to do anything more, because by process of elimination, it's got to be here. So what is the principle that I just used? What kind of algorithm did I just use? Anybody wants to tell me what kind of algorithm I just used?
Binary search.
Binary search. Right, so if I only have one single 1, it doesn't matter if I have 2 to the 63 minus 1. I can basically in 63 steps, more or less, tell you where the 1 is. Okay, with binary search. Because I can just cut in the middle. I can use the query to ask the first half, and then I can tell you whether to go in the first half or the second half. Okay, so what if there are more than 1 ones, right? They tell you that up to 1,024 ones. Okay, well, it's actually not that bad. So 2 to the 63 minus 1, I'll just call it A and B. It's a low and high. So low and high at the beginning. So mid, okay, we're going to compute mid. How do you compute mid? So first of all, the first thing that you realize is that these are fixed numbers. Okay, so you have to make sure that you use at least long for low and high, right? Low is 0, and high is equals to 2 to the 63 minus 1. How do you write 2 to the 63 minus 1? You'd say 2 to the 63 minus 1. But this won't work because this is going to be overflowing, because this is, when you just write something like this, 1 is treated as a 32-bit integer. So you actually have to write, you might then say, well, what about something like this, 1 long long. Well, it turns out that this also doesn't work because long long, it's a signed integer, and 2 to the 63 minus 1 is basically long long max. So when you say 2 to the 63, it's already overflow a long long. So what you really have to do is to say unsigned long long, because unsigned long long, the max is 2 to the 64 minus 1. Okay, so even computing this initially is a little bit challenging if you're not careful. And then you're going to have to do some sort of, when you do binary search, if you have a low and you have a high, you have to compute the middle. So how do you compute the middle? Does anybody know how to compute the middle in a binary search? Anyone? Nobody?
Would you just divide the length by 2 and then find that iterator in the middle?
So what do I write? What exactly do I write?
I would say, okay, what is your array's name? Sorry.
Sure, A. Let's go with A.
Okay.
Okay, there's actually
like-
no array here. I'm just computing an index.
Okay. Because I was just gonna say like a dot size divided by 2, but
Okay, but as I'm doing my binary search, this low and high will shift, right?
yeah.
So I don't always want the size, because if my high actually brings down to here,
Oh, I
binary
see what
search.
you're saying.
Yeah, so it's not always 0 to 2 to 63 minus 1, but as I do my binary search, the low and high can shift. So at some point, I need to know, at any point, if I have a low and a high, what is mid? So I guess this is kind of like there's a while loop in there somehow in the binary search. Okay, so I need to compute mid. So given the current values of low and high, how do I compute mid?
Just do high minus low divided by 2.
Hang on, let me write it not like this, because this is C++. High minus low divide by 2 like this. Is it like this?
I think so. I think so.
Okay, it's not quite right, because it could be that high and low are so somewhere in the middle, and so high minus low would just be kind of this length. Divide by 2 would be, so let's say this is, I don't know, 10 and this is 16, then high minus low divide by 2 is actually 3 over here. And what you really meant, well, I think what you meant to say is this, because you want 13, right?
Yeah. Math at night is hard for me.
Okay, yeah. Okay, now, there's also another way of doing it that's also very popular. Take the average of the two. Okay, so whatever it is, low, high, if this is, I don't know, 10 and 16, right? So 10 plus 16 is 26, so when you divide by 2, it's 13. One of them is good and one of them is bad. Which one is good and which one is bad? How many of you think that the first one is the good one? Okay. Anybody wants to virtually raise a hand or yell out if you think that this is a good idea?
Yeah, I think that one's good.
Okay. Anybody think the second one is good?
I think the second one was what I was thinking of the first time, but
Is there any
think-
difference? I guess that's the other question. Is there any difference? Why do I even bother telling you this? Why do I even bother showing you two ways? Right. So if I say, look at this thing, right? High minus low divide by 2 plus low. So if I, make it common denominator, then that's the same thing as, high plus low over 2, right? Mathematically, they look the same. Right? It's a slight difference because this divide by 2 is not exactly divide by 2 if there's a fraction involved, and with integer division, things kind of get rounded down. But mathematically, they're not that different. And it turns out that this is the good one, and the other one, I'm going to put a big red cross, even though you'll see this in textbook all the time. Okay, why am I writing this a big cross? In fact, this was in the Java binary search, in the standard library for binary search. When you call for Java binary search for a long time, it was implemented this way. And then one day, things broke. One day, that routine didn't work. And eventually it was traced to this. So why is this code bad? So if low and high are both sort of over here, okay, and you try to do low plus high, what's going to happen? It's going to overflow the 2 to the 63 minus 1. And then when you overflow, you probably get a negative numbers. And when you try to do index into a negative array, elements in the array, you're going to just crash. If you're lucky. If you're not lucky, your program keeps going, reading who knows what. But if you use the first one, high minus low is guaranteed to be in range. Divide by 2 is still guaranteed to be in range. And then when you add low to it, it's guaranteed to be in the middle. There's no way you can overflow here. Okay, so use this one. I know it's longer to type, and more complicated, but this one is the good one. The second one here, it's a bad one. I occasionally use the second one if I know for sure that I cannot overflow. But in this problem, because the numbers are so big, you can overflow with that, and you have to be careful. Okay, so you have to do this. All right, so that's the one important, I guess you can say minor, but very important detail. Because even if you get the rest of the algorithm right, if you didn't know how to compute the middle, something that looks so trivial and probably overlooked, even by the Java library developer, you'll get burned. Okay, so what are we going to do? The first thing that we're going to do is going to ask Q 0 and then 2 to the 63 minus 1, whatever that number is, because that's going to tell me how many ones there are in the whole array, because I didn't know that before. Okay, so that tells me the total count. And then I'm going to ask sort of the first half. I'll just write it like this, first half. Okay, so I'm going to ask the first half, and it's going to give me a number, whatever that is, some number of ones. So what do I know? If I know, of course, that whatever number they tell me, it's the number of ones here. But what they didn't tell me is that in this other part, the number of ones over here is the total minus whatever they just returned on the left half. And then I can recurse. I can recurse on this side. I can recurse on the other side. Okay. And every step, I would ask one question, which is how many are on the left half, and then I can recurse on both halves, because once I know the left half and I know the total count in the whole range, I would know what is the count on the right half as well. So I would have a recursive function called f, which will have sort of the low and the high, and also how many there are. So you tell me in advance, in this range from low to high inclusive, how many ones there are. And what would I do? So what would I do in this recursion? Well, if the count is 0, if you tell me this range has nothing, then I just return. There's nothing more to do. If the count is exactly high minus low plus 1, then basically add all the numbers from low to high. Okay, so if I have a range, if this is, I don't know, 0 to 10, and you told me that there are 11 ones in here, that means everything is a 1. The entire range is a 1. In which case, you know that all of these are 1s and you're done. Otherwise, if it's not these two extreme cases, then you have to do more. Then you basically say, well, ask Q low to mid. Okay, so Q low to mid. So basically cut the interval into first half and second half, and it will give you an answer, whatever that answer is, X. Then you can recursively do F of low to mid with X, and also F of mid plus 1 to high with count minus X. Okay. And that's basically the algorithm. That's all there is, really. And then, of course, once you've done all of this recursion, then you would have to basically look at all the numbers that you added and print them all out as the answer. Now, okay, so the code, maybe if you're not familiar with this kind of coding, maybe you don't know how to do the coding yet, but before I say a little bit more, is it clear what I'm trying to do and how this works? Is it clear why this will eventually give me the right answer? Maybe it's not so clear that I can do this in 2 to the 16 steps, 2 to the 16 queries. Okay, but we'll get to that. Okay, so how, if you believe that this works, so how is it that this is 2 to the 16 queries? So basically every query you can reduce the size of the intervals that you're interested in by half, right? So at the beginning, one query, you'll get the whole thing. Then you get another query, you'll get these two range. Then you ask 2 more queries on each half. You'll be able to say how many ones there are in each of these 4 quarters. So I ask 1 query, and then here I ask another query because I only have to ask the left half. And then I ask 2 queries because I have to ask the left half of this one and ask the left half of this one. And then I ask 4 queries, and I can figure out how many ones there are in each of these 8 intervals, and so on. Okay. So the next level will be 8 queries, 16 queries, and so on. Now, at some point, I'm going to have, okay, and the number of intervals. It's 1, 2, 4, and 8, 16, 32, and so on. So remember that I have at most 2 to the 10 bits. Okay, so how many steps do I, when I get to 2 to the 10, I now have 512, 2 to the 9 queries. So up to here, you ask this many queries, and you would be able to get basically 1,024 intervals. Now, many of these intervals, so it's possible that every one of these intervals would have exactly 1 once. And then you can do a few more steps to basically narrow it down, and you can figure out how long it takes to narrow down. But notice that as soon as you have an interval that is empty, so let's say that there's nothing in this, you don't have to ask any questions here. This branch is cut off. You don't have to ask again. And also, so in the worst case, if every single thing has a 1, if every time you divide, you have a 1. So in this case, down to here, you have 1,024 intervals. Every interval would have exactly 1, 1. That's the worst case. And then you say, okay, if you have 1,024 intervals, so 2 to the 10 intervals, you start with something that's 2 to the 63. Okay, that's the size of the original RAM. That means you will have 2 to the 10 intervals, each of size 2 to the 53. And then basically, it'll take you 53 more steps to zero it down. Basically zero in on where that 1 is. And so basically you add up the number of queries here to get you to this stage, which is about 1,023, I think, if I remember, if I add right, 1,024 actually, because I got 1 twice. And then I have 2 to the 10 times 53 steps to get down to the bottom to identify where the 1 is in each of those 2 to the 10 intervals. Then this is, I guess I can round it to 2 to this. This is a little bit less than 2, somewhere between 2 to the 5 to 2 to the 6. So this, it's somewhere between 2 to the 15 to 2 to the 16. And then plus the 2 to the 10 is not that much more. And if you kind of work it all out, if you actually, I guess, multiply, if you actually put it in the calculator, you'll realize that this is less than 2 to the 16. And this is the very absolute worst case. Okay, I don't know if that analysis you follow completely, but basically the idea is you basically keep track of what is the worst case. The worst case is if every interval you get, you still have to divide because both left and right have some 1s in it. Because as soon as you have a side that is completely 1s or completely empty, you don't have to subdivide and you can stop. So the worst case is if every single interval you have exactly 1, 1. And past the 10th level, you cannot do that anymore because they told you that they're at most 2 to the 10 1s. Okay, so that's quite complicated, but the code itself actually, it's not so bad. Okay, so first I decide that I use unsigned long long. So unsigned long long allows me to go from 0 to 2 to the 64 minus 1. Okay, so that way it's a little bit safer because I know that I don't need negative numbers anyway. So this gives me a little bit more room in case I screw up, but I'm not going to screw up, of course. Okay, so I have a function that basically asks the question. If I want to ask the question and see what the judge tells me, I just write a function that do that. So I print the Q, print the letter Q, print the beginning of the range, print the end of the range, and then this flush basically makes sure that the output is sent. So normally in C++, when you print things, it may not actually print. Your program may not actually print. It might actually decide to collect enough output. So maybe you only print, I don't know, 5 characters, and C++ decide that it's not actually that efficient. If every time you print 5 characters, it actually send it to the screen or to wherever it's receiving the output. So it might actually collect things until it has enough before it actually prints it. So this is called buffered input and output. So if you want to explicitly tell C++, please send everything right now, this is the way to do it. Cout flush. It flushes the buffer. Okay, so if you don't do this, it may be that the judge is just waiting for you to say something and you haven't said anything even though you executed statement because C++ is buffering the output, and then your program will just sit there forever. Okay, so I print the query and then I read in the answer from the judge and then I return it. So this function just basically asks a question and returns what the judge tells me. Okay, so the main code is like this, low and highest as I say. Then I have answer is, so I just ask the entire range. So this gives me the total number of ones. Then I call this recursively, okay, on the whole range. And then I print the answer. So I have a set. So I have a set of addresses, and I'm going to add in my recursive code, add all the addresses. So at the end, I've collected all the addresses that has ones, and then I just print out the addresses. So the magic happens in the recursive function. So here, if the count is 0, I don't do anything because if the range is empty, there's nothing to do. And if for some reason my 2 pointers ever cross, I don't think that will happen, but this is just me being, I guess you can call it defensive programming, just in case. If these two things ever cross, then I also quit. Otherwise, basically if the count is exactly the size of the range, that means everything in that range is 1. So I just loop through this range and add it to the set. Okay, and I have to be very careful to declare things as unsigned long, and not int. In fact, this is our team 1 in the division 1. They actually got this whole thing right, except that they screwed up by writing ints right here, and then they got an overflow here. If they fixed just that, they would have gotten it correct, but they never did get it accepted in the real contest. Okay, so anyway, if it's not any of these base cases, then the only thing I can do is I have to do something. I have to ask a question. Which question do I ask? I figure out the middle. I ask what is on the left half from low to middle. And then I recursively go to the left, and I recursively go to the right. And that's it. That's the code. So if you ever see one of these interactive problems, you can probably bet that, there's a very good chance that there's some kind of a binary search that goes on in there, because that's kind of the standard thing that people can do when there's some kind of interaction. It's like what do you call it? The guess a number, right? Guess a number between 0 and 99 or whatever. Anyway. Okay, so that's that one. Now, I think that most of you, at least most of you, maybe everybody here, have never seen an interactive problem before. And it's actually quite fun, right? Because there's a little bit more going on. You have to kind of figure out what to do from one step to the next, and then change your response based on the previous response. But it requires a little bit of different thinking. Okay. Any questions? Okay, what time are we at? 8:34. Okay, now, which one do I want to talk about? Maybe this double agent conference is easiest to talk about. I know there's a lot of text. Okay, so Reed there has finished organizing this year's double agent conference. The conference consists of a morning event, an afternoon event, and an evening event for local double agents to attend. Reed wants to know how many double agents attended at least one event. So I set up a booth for the double agents to check into before each event. Each double agent checks into an event by scanning a finger, which the system associates with a unique ID number. For extra security, no one can leave any event after it starts, so that no one checks in twice to the same event. Reed thought he'd cover all the possible loopholes to ensure correct count of attendees until he realized that the same double agent could scan a different finger at different events, so that two distinct ID numbers could correspond to the same person. Okay, so for this year, Reed was settled for knowing the minimum possible number of distinct double agents who attended at least one event, given that each pair of ID numbers from the same events correspond to distinct double agents. So if you have the same morning event and you get different numbers, then you know for sure that those people are different. And that each individual ID numbers always correspond to the same double agent, because no two double agents share identical fingerprints. So in the first sample case, what is the first sample case? It says that you have 3 people attending this morning sessions, 2 people in the afternoon, and 2 people in the evening, and these are the IDs of the morning, afternoon, and evening. So you know that the morning, there's definitely 3 different people. The afternoon, there's definitely 2 people. Evening, there's definitely 2 different people, but this 3, for example, could have been the same as 0. It could just be the same person. So in the first sample case, one double agent might have attended all 3 events and scanned 2 different fingers, so that the system registered this freaky double agent with 2 numbers 0 and 3. Since all ID numbers in the same event correspond to different double agents, 3 distinct double agents attended the morning events, so at least 3 double agents attended at least one event in the conference. Okay, so they give you up to 100,000 people in each of the events. The IDs are non-negative integers, strictly less than 100,000. So you have at most 100,000 IDs to deal with. And you have to figure out based on this list of IDs, how many people for sure attended, how many different people for sure attended some event. Okay, so that's the question. So what do we know? You have the morning events. I'll just call them A, B, and C. Morning, evening, and dinner, and then evening are just 3 events. So you might have some IDs that may attend only the morning. Maybe you have some ID, right? So maybe you have another ID that attends only the afternoon. Maybe you have some ID that attends morning and evening. Maybe you have some ID that attend all 3 of them, and so on. So let's say you have this situation, right? You have, what do you know about person 3? What do you know about person 3? Can it be any of these other people?
Three can't be 0 or 2
Or 1?
or 1.
3 cannot be anybody else.
Because he attended all the events.
Okay, 3 cannot be anybody else. Okay, anybody that attended all 3 events cannot be anybody else. Okay, because they will conflict with, they will always have somebody else. Whoever else attended any event, they will always be different. Anybody that attended all 3 events are different. So the number of people that attended all of ABC, I'll just write it ABC. The number of people that have attended all 3 has to be the number of people, they definitely attended something. And they cannot be the same people as anybody. So you can always count them. Okay. Okay, let's try some other possibilities. Maybe there's some people that only attended the first 2 sessions. There might be some people that only attended the last 2 sessions, and so on. If I look at people that attended 2 sessions, they can attend sort of in different ways. Okay, maybe you have another one that attend these 2. these people that attended two separate sections can never be the same as any of these other people, right? So this person attended A and C. This person attended A and B. There's always going to be some section that they both attend. Okay, whenever you have somebody that attended two sections, you take two of these people together, there's always going to be some section that they both attend. And so none of these people can be the same person. All of these are people that are guaranteed to be unique people. Does that make sense? Now, what about the people that attended only one section? Well, now you have problems, because this one here, maybe it's the same as this one. Maybe these two people are the same, right? Because there's no conflict between, they don't attend anything in common. So it's possible that 1 and 2 are really the same person. It's also possible that 1 and 6 are the same person. Basically, somebody that attended B only and somebody that attended A and C may be the same people. Similarly, the number of people that attended just A may be the same people as the same people that attended B and C. And the people that attended just C may be the same people as the people that attended just A and B. So what to do? Well, let's imagine that you have 3 people that attended only A and only 1 person that attended B and C only. Well, in that case, you know for sure that 2 of these, that 1 of them might be the same person, but 2 of them are not. It could be that you have 2 people in this group that are actually, at least 2 of the people are not one of these people. Similarly, if this is, I don't know, 5 and this is 3 or 2, then you know that 3 of these people are definitely not these people. And then finally, let's imagine that you have, I don't know, 1 and I don't know, maybe you have 7 people. Then you don't know. If this 1 person could be any one of these 7 people, so there might be no people in this group that are unique. So what we do is we take the number of A's minus the number of B and C and subtract them. And if it's negative, you just make them 0. Okay, so if negative, set to 0. Okay, because in this case, 1 minus 7, I'm not going to count -6. I'm just going to say nobody that attended C, I can guarantee to be a unique person. So here in my case, I have 2 people from the people that just attended A that I know is not one of these people, BC. I have 3 people in this group that I know is not going to be AC, and I have nobody in this group that I know is not AB. So I have these numbers. But these 2 people can actually be the same people that attended B. That's possible. There's nothing that says if somebody that only attended A, they might also attend B using a different name. So if I look at this, how many unique person can I have? The answer is that at most 3 unique people. Basically, I take the biggest number, and that's the number of unique people I have. because everything else could be matched. They can potentially all match with each other. So if you've been following this argument, then the final answer is the max of A minus BC, B minus AC, C minus number AB, and 0, because it's possible that all of these are negative. So if you figure out how many people attended all three, how many people attended AB, only AB, how many people attended only AC, BC, and how many people only attended AA, B, and C, then this is the final answer. It's a long formula, but that's how you count the number of people that must, the minimum number of people that must appear. Does that make sense? Yeah, you might have to think about it a little bit. And then maybe the next question, the last question, I suppose, is how do you know how many people attended all three, how many people attended just the first two, and so on? Well, there are lots of ways you can do this. I mean, you can have an array of three, I don't know, Boolean array, three-dimensional, I guess, sorry, 3 rows or 3 columns the way I draw it, but you can have 1 column for each event, and then the row, 1 row for each person, and you can mark it the same way that I do it. Or you can say, let's represent each thing as a binary number. So A, B, and C are basically 3 bits. If you attend it, it's 1. If otherwise, it's 0. So this would be 1, 0, 0 of 4. So these are the numbers in decimal, and binary, of course, is you can think of as 1, 0, 0, 0, 1, 0, 1, 0, 1. It doesn't actually matter which bit you use for which. I think actually in my code, instead of ABC like this, I actually use ABC like this. It doesn't really matter. It's as long as you know which bit is used for what, it's good enough. So let me just quickly show you my code. Okay, so I read in the number of people in each session, and in fact, I just use an array of 3 things to store the number of people in each session. Then I have this binary mask that I'm going to use for each person to remember which set of sessions did they attend. And at the beginning, all of them are 0, meaning at the beginning, all of them attended nothing. For each sessions, I loop through all the participants. I read in the ID of the participants, and I go and turn on the I bit. So if I attended the 0th event, so this was a morning event, I turn on the least significant bit. If I is 1, then I turn on the middle bit. If I is 2, I turn on the most significant bit. And this basically sets for each person a bit mask that tells me which event they attended. Then I just count them. So basically I have 7 counts that I care about, 1 to 7. So bit mask is from 0 to 7. I actually don't care about the bit mask of 0 because that just means they didn't attend anything. But anyway, I just go through all the people and I just collect the mask. So mask of, so here count 7. 7 is 1, 1, 1 in binary. So that's the count of all the people that attended all 3 sessions. And then these 3 are the counts of people that attended 2 sections. And then this is 0, 0, 1 and 1, 1, 0. So attended 1, and then this attended the other 2. Right? It is another attended this one, and then the other 2, and then finally this and this one. I take the maximum. I take 0. I have to do this in a funny way because in C++, you can only do a max of 2 things. So if you want to take the max of 4 things, you have to kind of chain your maxes together, right? So that's basically what I was doing. So that's it. So this problem is much less about coding, I guess, and much more about thinking carefully what's happening. And I guess that's really all I can say. Are there any questions? Okay. All right. Now the next one, I'll just kind of quickly go over this because I don't want to maybe spend too much time talking about the code. So there's a big story. Okay, but anyway, you have a 3D object. Okay, so you have a block like this, and they give you the front view, the right view, and the top view. And all you see is whether there's something there or there's nothing there. Okay, so this object, you see what's in front. It looks like, from the front, it looks like this. From the right-hand side, it looks like this. And from the top, it looks like this. And then you have to, so you're given this, this picture. So this is the front. This is the right. This is the top. And then you have to figure out either that the thing that the views that they give you make no sense, in which case you say invalid, or what is the volume of this thing? How many pieces are actually on? Now, they do say the actual volume may be less. For example, if the objects were hollow, but there's no way for math to tell from the pictures alone. So you're just going to tell the maximum possible volume. So I guess I'll just kind of briefly explain what you have to do. And the coding is a little bit messy. So basically you have a 3-dimensional array of blocks. Okay, so in this case, it's 4 like this. And then that's 3 this way. And at the beginning, you say that everything is on. Now you look at this and you see that from the front, it looks like this. Now it doesn't mean that it's a T in the front face. It just means that when you look this way, you will see something in this, somewhere in this block, somewhere in this column, in this set of blocks, and so on. So you can't really say too much about where things are, but what you can say is where things are not. Okay, so what do I mean by that? You know that you have these 3 white spots. So when you see these, when you see those 3 white spots, what you can do is you can actually go and wipe this whole thing out. This whole column, you know there's nothing there. Same thing with this one and same thing with this one. In other words, you can actually just go and carve it out. You know there's nothing there. But when you see the black ones, you actually don't know where they are. Okay, now you look at the right view. You see that there's nothing in this corner. That means you can cut this whole thing out. None of this is part of it. And then when you go on top, you see that these 6 places are off. So you can kind of carve this chunk out. You can carve this chunk out. And you can carve this little down. And you carve this one down. And the carving basically allows you to clear a whole line of blocks. And that's the first step. It's to go through these things and figure out whether you have the white block, and then you just kind of slice them by setting them to 0. But what happened though is that if the top and bottom, top and front and right view are not consistent, it's possible that when you carve things out, you carve out too much. So the second pass, what you have to do is you have to go through these views again. And when they say, let's say this one is black, let me change the color. So they tell you that this one is black. What you have to do is you have to look this way and make sure that there is actually something there. Because, for example, if the right view image looks like this, and then because the right view image looks like this, you actually go and carve out the whole top row, whole top slice, then all of this would be inconsistent because there will be no black one. So what you do is that you look at these views, and for each black one, you scan that line and make sure there's at least one black. You don't care where it is, you just make sure that there's at least one black. If any of these ones don't have a black at all, then you know for sure that it is not going to be, it's not valid. So you do all this check, and if it's still valid, then that's it. Then you're done. That means that everything's consistent, and then you just count how many black blocks are still left, and that's the volume. Okay, so the code is a little bit messy because you have to worry about, you have to worry about going at each direction, and then if you're going in front, you have to slice this way. If you're going to the right, you have to slice this way. If you're going top, you have to slice down. And you can, of course, if you want, basically write the same code 3 different times with one, basically each time doing slightly different things based on the direction. But that would not be very good. So my code, and this is on the GitHub if you want to look at it, actually try to do a little bit smarter. I would say, or I will only say try. So the carve function basically loops through all the things on the view, whether it's top, bottom, top left, or sorry, top right or front. Try to set some parameters, and then my main loop, it's the same regardless of which way you are, but I basically set some sort of ways to move through with this dx, dy, and dz. So if I'm moving this way, if I'm moving in certain direction, I might say dx and dy is 0, and dz is like +1. And then if I'm going down, so my coordinate system, I think, was something like, how does it go? I think the way that I did it was, this is x, this is y, and this is z. But it doesn't really matter which way you do it. You just have to make sure that you keep things consistent. So if I'm going down, I might say dx and dz is equals to 0, and then dy is equals to 1, and so on. And basically carve out most of the code is to figure out. So if I'm in the view and I see a black one, I continue. Otherwise, it's empty, so I have to carve things out. So I have a lot of code to set up how I want to loop. But basically, I loop. As I loop, I just set it to 0 to carve it out. And then I have some debug statement to make sure that I'm carving out the right thing. And then check is really the same code. So it's pretty much the same code, but this time, if I see a pound, so if I see a dot, I continue, but if I see a pound, I loop through and I see if I can find a block that is set. So this is my final check. If I see a pound sign, then I need to look down that line and make sure that there's at least one block that is set. And then if it's not found, that means it's not valid. And then my main code is kind of like this. I read in the 3, but at the beginning I set the whole thing to be solid. I read in the 3 phases. I carve with different parameters. Then I check the 3 sides to make sure that if I have a pound, there's really something there. And then if it's not valid, I print invalid. Otherwise, I add it all up. to give me the final volume. So this one is definitely a little bit of work in terms of coding. The actual idea is not so bad if you keep your head straight and make sure that you don't get confused, but it is not super easy, that's for sure. So let's see, let's go to D1, which is the division, the official contest. If we look at the standings, so there are a bunch of people that solved all 10 problems. Wait here. Okay, so most of these people are actually from UBC. So they're not in our region, although I guess they are still in the same division championship for those that are moving on. Brandon Fuller Fan Club. Brandon Fuller is actually an alumni of ours, and this is actually the U of A team that won the regional, and they solved everything eventually. And then this is the U Calgary team. Our team didn't do so well, but then we also got broken up into 2 different parts. At the end, I guess the two of them combined together solved 5 of the Division 1 problems, although it's a little bit tricky to count that way because some problems are solved separately. So who knows? Anyway, so those are the problems. In the actual statistics, the number of people that solve this one is really large. Star battles, of course, and then it kind of pretty quickly drops down. But the ones that I talk about, I guess, are the easiest problem. Okay, I guess it's coming up to 9 o'clock. Okay, so now I want to say a little bit about how we're going to do things from now on. So for most of you, I guess for everybody that's actually here, you don't really have an official contest for a while. If you're thinking about participating in regional contests, that's going to be a while longer. Who knows when the next round of regional contests is. So what I've decided to do is to set up these basically week-long contests that you can do, and we'll talk about it next week, kind of like how we did it at the beginning. But I want to choose problems that every week there's a theme. So there's a theme in this week's contest. I'll post a link in Discord so you know which contest it is. And I want to maybe every week try to teach a little bit of different topics. Now for this week, I already chose the problems. But for future weeks, if you want to tell me you want to learn something, you want to learn this or you want to learn that, maybe if, I don't know, in 3620, let's say that in 3620, maybe you're learning Dijkstra's algorithm and you want me to choose a Pope-Howler problems that have something to do with Dijkstra's algorithm, just send me a note. I can do that. I don't mind that. And basically my idea now to prepare you for the next round of contests is to kind of show you all the different techniques. So far, maybe the last little bit, I've been showing you contests, and they're kind of all over the place. You have a little bit of this, a little bit of that. If we try to do a theme, more focused set of problems, so this group of problems, I will even tell you, it's all about data structures. So using data structures in a certain way. These are, I think, for the most part, data structures that you hopefully know, but maybe you haven't really used it a great deal. So I'll just leave it at that, and then next week we can talk about these problems. And as usual, I put all my code on GitHub, so I'll solve all of these and put them on there so you can look at it later. I haven't actually solved any of them yet, but I will. Okay, so that's all I have for this week. Let me